Welcome to the Explainer. Today, we're cracking open the Mathematician's toolbox to get a handle on one of its most powerful and maybe most intimidating tools, differential equations.
But here's the thing, we're not just going to dive in and start solving them. We're actually going to do something way more fundamental, learn how to identify them. We'll look at how they describe change, how we perform a proper diagnosis on them, check out the specific tools for first-order and second-order types, and really nail down why picking the right tool is, well, everything.
Okay, so let's just dive right in. How does math even begin to describe a world that is always, constantly in motion? I mean, everything from the way a disease spreads to the orbit of a planet to the money in your bank account. It's all changing.
Well, it does it with these things, differential equations. The secret sauce, the one ingredient that sets them apart from the algebra you're used to, is that they contain derivatives. You know, y prime, dy, dx, all just fancy ways of talking about a rate of change. So, if an equation has a derivative in it, boom, it's a differential equation.
And they are literally everywhere. We're looking at a page here from our source material, some handwritten notes that are actually describing a pretty simple electrical circuit. Now, it might just look like scribbles, but what it shows is how these equations are the hidden language of the universe. They model everything from the current in this wire to the path of a comet through space.
Now, think about it like this. A good mechanic doesn't just start replacing parts on your car, right? First, they run a diagnostic. The same exact principle applies here. To solve any differential equation, the very first, most critical step is a diagnosis. You gotta know what you're up against before you can even think about which tool to grab from your toolkit.
And that diagnosis? It's a simple three-step checkup. We figure out its type, we figure out its order, and we figure out its linearity. If you can nail these three things, you are honestly halfway to finding the solution.
So, first up is type. As you can see in these notes, differential equations pretty much split into two big categories. Ordinary, what we call ODEs, and partial, or PDEs. For our purposes today, we're zeroing in on ODEs. Those are the ones where the function we're looking for only depends on one single variable, like time or distance, but not both.
Next, we check the order. This one's a gimme. It's the easiest step. You just look for the highest derivative in the equation. See a y double prime? It's second order. Easy. But then comes the big one, the most important test, linearity. And this isn't some vague feeling. It is a very strict diagnosis with very specific rules.
And here's the deal. For an equation to get that linear stamp of approval, it has to pass all three of these tests. First, the unknown function y and all its derivatives, they gotta be to the first power. No y squareds allowed. Second, you can't have y and its derivatives multiplied together. And third, y can't be trapped inside another function, like a sine or an e to the power of y. If it fails even one of these, just one, it's nonlinear. And that tells us we need a completely different set of tools.
Okay, so let's open that first tray of tools and see how this all works in the real world. Once we've done our diagnosis and we know we have a first-order equation, how do we pick the right screwdriver for the job? This table right here, this is our field guide. This is where all that diagnostic work really pays off. You look at the structure of the equation you have, and you match it to a tool on this chart. So if you spot a linear equation that fits that top form, without a doubt, your go-to tool is the integrating factor. If it looks like a Bernoulli equation, your tool is a clever substitution. See? The diagnosis points you straight to the method. So let's take a closer look at the tool for a standard first-order linear equation, laid out here in these notes. The master key is this special function they call the integrating factor. It's like magic. You calculate this thing, you multiply it through the entire equation, and poof, it transforms one side of the equation into something you can integrate almost instantly. It's incredibly elegant. Oh, and Bernoulli equations. These are a perfect example of this whole toolkit idea. At first glance, it looks nonlinear, right? It's got that y to the n term trying to trick you. But it's just a disguise. With one little substitution, you can transform the whole thing into a standard linear equation, a problem you already have a tool for. It's like a mathematical judo move. You use the problem's own weird structure against itself. It's brilliant.
All right, time to level up. We're moving on from the first-order stuff to a new set of tools. These are designed for a super common and really important type of problem, second-order linear equations that have constant coefficients.
And what's so amazing here, as you can see in these notes, is that for this entire class of problems, our main diagnostic tool is something you probably learned in high school algebra, a simple quadratic equation. We take our differential equation and we morph it into this thing called the characteristic equation. And just by solving this basic algebra problem, we learn everything we need to know. The answer isn't just a number. The answer is the blueprint for our final solution. The nature of those roots, we call them lambda 1 and lambda 2, it dictates the exact structure of the function we're looking for.
And get this, there are only 3 ways it can go. That's it. Case 1, the roots are real numbers and they're different. Case 2, the roots are real, but they're the same. Or case 3, the roots are complex numbers. And each case has its own pre-built template for the solution. It's really like a choose-your-own-adventure for solving equations.
And here you can see it all in action. On the left, you've got a problem whose characteristic equation gave 2 different real roots. The solution is just made of simple exponential functions. But on the right, the roots were complex, and look at that. The solution is built from sines and cosines, the language of waves and vibrations. The diagnosis determines the destiny of the solution.
So we've talked about types and orders and toolkits. But what's the big takeaway here? Why is spending all this time just sorting and classifying equations not just important, but actually everything? It's because, as our source material says so clearly right here, you don't just jump in and start calculating. The very first thing you think about is, what am I looking at? Is it linear? What order is it? Answering those questions is what tells you which tool to reach for. It's all about strategy before tactics.
Ultimately, the real elegance of differential equations, the real beauty, isn't just in finding the final answer. It's in the methodical diagnostic process that gets you there. It's about recognizing the pattern in the chaos and knowing exactly which tool to grab for the job. So, with a whole universe out there just waiting to be described by these equations, what change would you want to understand first?